Hello friends, in this video I'd like to solve the following problem from the Hellenic Mathematical Olympiad final round 1996, problem number 4, from combinatorics you can say. Find the number of functions f from the set 1, 2, 3 and so on up to n into the set 1995, 1996 such that this sum f of 1 plus f of 2 plus and so on up to plus f of n is an odd number. So my hint for this problem, first of all, if we know that sum of some integers is odd, something can be said about the number of these terms, how many terms are odd and how many terms are even, about the parity. And also the binomial theorem may be useful. You shall see in a moment. Okay, so I hope that you've managed to solve this problem. First of all, crucial observation. We have only two possible values, so here we have our values, and here we have a bunch of arguments on the left hand side, let's say, and some of these arguments will go to this number, the rest will go to this number. And the crucial observation, adding even terms to our sum doesn't change the parity, but adding odd terms changes the parity. Moreover, it should be pretty easy to see that the number of terms, the number of arguments which go to this number must be odd. So in this set, in this blue part of the domain, there must be odd number of elements. So in other words, the preimage of 1995 must have an odd number of elements. If you are not familiar with this notation, f minus 1 of some set, it just means all the arguments such that f of x is in this set. So these are all the arguments which go to the value of 1995. Okay, so we just need our entire domain has n elements, and we just need to point out, to select odd number of terms. So either 1 term, 3 terms, 5 terms, and so on. In how many ways can we select an odd number of terms from n elements? Well, one element can be chosen in choose one ways. 3 elements can be chosen in n choose 3 ways. 5 elements can be chosen in n choose 5 ways, and so on and so on. This sum is finite, but the last term depends on the parity of n, so I will leave it at that. So now we just have to evaluate this sum of binomial coefficients with odd lower indices. Okay, how can we do it? Well, the binomial theorem can be quite useful, because by the binomial theorem we have the following. We know that 2 to the power of n, which is 1 plus 1 to the power of n, it's just the sum as k goes from 0 to n of n choose k, and 0, which is 1 minus 1 to the power of n, is the sum which goes from 0 to n of n choose k minus 1 to the power of k. The first equation holds for every non-negative integer, the lower holds for positive integers. But we are dealing with positive integers, so it's good. And now let's notice that if I if I subtract these equations, I will get 2 to the power of n equals, so maybe let's write this sum in other way without sigma. It's n choose 0 plus n choose 1 plus n choose 2 and so on and so on and so on. And the lower sum is n choose 0 minus n choose 1 plus n choose 2 minus and so on. If we subtract these equations, we will be left only with 2 times n choose 1 plus 2 times n choose 3, 2 times n choose 5, and so on and so on. And that means, after division by 2, that our sum is 2 to the power n minus 1. And that's our answer. There are exactly 2 to the power n minus 1 functions which satisfy our conditions. Okay, and now, as a little bonus, as a little addendum to this video, I will present another solution, more combinatoric in its nature. Well, because let's notice, how many functions are there from n elements to 2 values? Well, 2 to the n. And this is exactly 1/2 of 2 to the power of n. So exactly 2 to the power of n minus 1 functions satisfy our condition, and the same number of functions do not satisfy our condition, which suggests that we can establish that number of functions which satisfy our condition by constructing a suitable bijection. And I will do that in the second part of my video. Another solution. Another solution goes like that. So, for the sake of brevity, I will denote by capital X the set of all functions, f from 1, 2, and so on to 1995. Running out of space. Oh no. 1995, 1996. Okay. Believe that I've got it right. And now let's further consider subsets of x sub 0. The number, it's the set of all functions f from 1 to up to n such that 2 divides f of 1 plus f of 2 and so on plus f of n. And finally, let's consider the complement of this set. Consider the complement of this set. X sub 1 will consist of all the functions whose sum f of 1 plus f of 2 and so on is not divisible by 2. Okay. Now, I will construct a bijection from x0 on to x1. And that will prove that these two sets have the same number of elements. And moreover, since there are 2 to the power of n elements in total, that will mean that both of these sets must have 2 to the power n minus 1 elements, exactly half of the elements. And this bijection will go like that. I will call my bijection capital psi, and it will take a function, it will take some function from x sub 0, and it will put a modified function from x sub 1. And how does this function work? Well, it takes argument n, and I define it as n if n is no, n was already used, so let's call it k. If k is less than n, and finally it will be 1995 if k equals n and f of 9995 equals wrong, and f of n equals 1996, and it will be 1996 if k equals n and f of n equals 1995. Okay, so basically the idea is I now consider a function which behaves exactly like f with one exception. The final value is flipped. So if the final value for argument n of our function f was 1996, I change it to 1995. If it was 1995, I change it to 1996. And now observe the following. This function is properly given. What I mean by that, the values are in reality in the set x1, because if sum of all the values was even, then by changing the parity of the last term in our sum, the parity of the entire sum will change as well. So this function is properly described, domain is well given, and codomain is also well given. Moreover, this function is a bijection. Why? Because let's notice the following fact, that if I consider the same function on the set x1 from to x0, it's given by the same formula. Let's notice that psi composed with itself is just identity of our set. Because if we change twice the last value, it goes back to its original form. So let's summarize. Psi is a bijection. It's a bijection, and the image of x0 is contained in x1, psi of x1 contained in x0, and that means that psi is, that means, to be honest, by the first line I mean the function psi which goes from x to x. This function is bijection. These two inclusions are true, and that it should be pretty easy to check that means that these sets have the same number of elements. And in turn, since since the cardinality of set X was 2 to the power of n, it must be true that the cardinality of x1 is 2 to the power n minus 1. The exactly same answer. In a combinatorical, more theoretical way, I'd say. Okay, so thank you for watching. I hope that you learned something new. I hope that you enjoyed my talking. And see you next time. Goodbye.